and this is the project I've been working on about quantizations of classical field theories and anomalies. I'd like to thank Dr. Saki Koizumi for all her help with me over the last 8 weeks. So before we get into quantization, we first have to discuss a little bit about our classical field theories.
Yeah, should work just no. Yeah, sure.
Yeah.
Okay.
So we first have to just discuss just a little bit of background on classical field theories. So in general, a generalized set of coordinates, Q, can be used to describe the state of a system, where the mechanics of the system are then described either by the system's Lagrangian, which is a functional of the generalized coordinates, generalized velocities, and time, or it can be changed to the Hamiltonian, where generalized momenta replace the generalized velocities. Also, the Lagrangian of a system will define its action, which must have zero variation from the principle of stationary action. And just an important quantity to define for classical field theories is the set of Poisson brackets for two functions or two functionals. The convention that I work with is given in this form here. So in classical field theories, some systems will have a symmetry, which is a transformation of the coordinates or of the time that leaves the action of the system unchanged. And from these symmetries, we get Noether's theorem, which says that if the action of a system is invariant under a continuous symmetry, then there must be some conserved quantity. And these conserved quantities are known as Noether charges or observables, which can be something like energy or charge or angular momentum. So just an example of this for the classical theory of the 0 + 1 dimensional Klein-Gordon field. So we only consider the time dimension, no spatial dimension. We have generalized coordinates given by phi and phi dagger, which are functions of time, where time is on the 1 sphere. These also have conjugate momenta given by pi of t. So while these are complex fields, we can replace them with real fields given by q plus and q minus, and we can rewrite our Lagrangian in terms of our new real fields. We also have new real conjugate momenta, which are shown here. So computing the Poisson brackets between our generalized momenta and generalized coordinates, we can see the only one that will return anything non-zero is when they're both in the same phase, or when they're both plus or minus for Q and our momenta. There's also a U1 symmetry applied to our fields phi, and clearly from the Lagrangian is unchanged under this transformation of coordinates. So this gives rise to a Noether charge, shown here by Q phi, which is exactly the conservation of charge of the system. And computing the Poisson bracket between the Noether charge and our fields and our momenta gives actually the variation of these fields when they undergo this symmetry transformation. We also have a time translation symmetry, where our variation in time is given by some epsilon. And we can see that our variation of our generalized coordinates is given here by minus epsilon phi dot and minus epsilon phi dot dagger. So when we compute then the overall variation of our Lagrangian, we can see it's in fact it's proportional to a total derivative with respect to time of our Lagrangian, which again implies that there's a conserved charge. And this conserved charge is actually exactly the Hamiltonian of the system. So that means that this conservation is the conservation of energy of our system. So the Hamiltonian gives us exactly our energy of our system. And we can see here then when we compute our Poisson brackets between our Hamiltonian and our momenta and coordinates, it gives us actually the variation under a time translational symmetry of our coordinates and of our momenta. And this is important for our equations of motion of these coordinates and momenta. We can also define some functions a plus and minus and their complex conjugates. These are more important for when we quantize, but they end up being our creation and annihilation operators of our quantum system. So one way we can promote this to a quantum field theory is by using a canonical quantization. So first we must define a Hilbert space on which operators of this system act. So we know from quantum mechanics that we can promote our generalized coordinates and momenta to operators q hat and p hat, which should obey the canonical commutation relations shown here. This we know from general quantum mechanics. And then once we promote as well our creation and annihilation operators, we should get commutation relationships where the commutator between one of our creation and annihilation operators for the same mode should equal 1, and they should be 0 in all other situations. And our Hilbert space is defined by these creation and annihilation operators acting on our vacuum state at some time t, given by the ket of 0t. So our Hilbert space is the total set of all states where there's creation and creation operators acting on both positions, plus and minus, where n and m are both natural numbers. We can also then work out we can promote our Noether charges to operators, which themselves are invariant with time when we look at a case of our time translation symmetry. So this allows us to compare the commutator of our Hamiltonian with our coordinates and our momenta. And again, it gives similar results from our classical theory to promoting them to operators. So there's two ways we can look at varying our Hilbert space from this type of quantization for time translation. So if we follow along by changing directly the time coordinate and carrying that change through all of our momenta and our position operators, we can see we're left with a set of states n and m, which is dictated actually by our original creation and annihilation or creation operators, plus some variations. But these variations are actually exactly the commutator between our Hamiltonian and our original creation and annihilation operators. So these are two different ways we can look at the variation of Hilbert space with time, but they're both identical, they're both equivalent. The issue with canonical quantization, however, is it's very physically motivated in the sense that we know what things should look like from quantum mechanics, but it doesn't give us a rigorous method of defining our Hilbert spaces or operators. So now I'd like to look at geometric quantization, but before that, there's a little bit of differential geometry we need to cover. So firstly, we have this manifold, a symplectic manifold, which is a 2n dimensional manifold spanned by coordinates of position and momenta, or their generalized coordinates and their conjugate momenta. And there is a symplectic 2 form, which is non-degenerate and closed and antisymmetric. In general, the simple case is given here by omega. This isn't always true. However, by Dabrow's theorem, you can always find an open subset of a manifold where this is true. So it's the only case that I'm going to consider. We also have tangent bundles. So tangent space is spanned by some tangent vectors of a manifold, where our tangent bundle is then at some position p on the manifold, and our tangent bundle is the overall collection of all of these tangent spaces. So a little kind of visualization is shown here, where if we have some manifold along the bottom, our tangent space or tangent bundle is above this manifold, and at some point p, we have a one-dimensional complex vector space given by our tangent bundle, or tangent space. We also, similar to this, we have a line bundle, where if we have some manifold L above our original base manifold M with a mapping pi, which brings us from our line bundle to our base manifold, there has to be, for every P on our manifold, a mapping from all points A on our line bundle. So this is very similar, except it's not as specific as our tangent bundle where it's spanned by tangent vectors. It's just some other manifold above our base manifold. But it comes with these things called sections, which is a mapping from a subset of our base manifold back to our line bundle, such that the composition of our line bundle and some section gives an identity on our base manifold. And finally, we have a connection, which is a collection of maps on a line bundle with a covariant derivative operator, which has a few properties in terms of functions and vector fields shown here, where L of x is the Lie derivative of some function. So when talking about geometric quantization, we have to discuss when is a system quantizable. So if we have a symplectic manifold M with a 2 form omega over it, and if there exists some line bundle pi where the curvature on our line bundle of our connection is equal to this 2 form, we say that the system is quantizable. So we can see this a little bit here if we take some simple phase space M with an associated two-form omega, and it also has a symplectic potential, which is a one-form A given here. So if this is true, we want the curvature of our connection on our line bundle above this manifold to be equal to this omega. So we have Hamiltonian vector fields of some functions on M given by x of f, which in general are functions of position and momenta and spanned by tangent vectors. And then the contraction of this with our one form is given in general here. This is just a little bit to clarify what will happen a little bit later on. But if we let our pre-quantization line bundle L just be the trivial line bundle, so the complexification of our base manifold, all sections on this line bundle can be given in the form of some smooth function f multiplied by our unit section S1, which we can fix. So then all of our variation is in this smooth function f. For this trivial line bundle, the connection can always be written in the form of a Lie derivative of some function minus some one-form contraction against a vector field. And when we compute the curvature of this connection, we actually do in fact get that our curvature is equal to the exterior derivative of our one form, which is exactly our connection. So this system would be quantizable. And the pre-quantum line bundle is then our manifold L pre with our connection nabla. So that means then we can define our pre-quantum Hilbert space simply as just the set of all the sections over this line bundle L pre. However, we can also define what we call a pre-quantum operator. So if we compute the variation of the symplectic potential with respect to some vector fields xf, we see that we get an exact one form. And this again is a symmetry similar to how when we've computed in the classical case, the variation of our Lagrangian with respect to time, we got an exact derivative. This means that there is a symmetry here on our connection. And that means that we can define a pre-quantum operator given here by Q of f, where the addition of the multiplicative term actually removes the variation and it returns an exact derivative again. So using this operator, we can see that we actually do in fact get back our canonical quantization, our canonical commutation relations, which is good. It means that this method has given us something physical back. The one issue with it so far, however, is that if we look in general at the form of these sections, we can see that they're functions of both position and momenta, which means that the sections depend on two n variables as opposed to n, which we would expect from general quantum mechanics, which means that our Hilbert space is not irreducible, which means there's a subspace that can equally define or equally explain all of this physics. So if we want to properly quantize this system, we need to not have H be irreducible, or we need H to be irreducible. So one way we can do this is with polarization. So if we have some complex linear subspace of our vector space, then with an orthogonal vector space given as shown, if these two subspaces are equal, we say it's complex polarization of this vector space, which is a little bit abstract. I'll go through an example afterwards, which will make it a little bit clearer to see. But if we have some complex polarization, then for any vector fields x in our complex polarization, the Lie derivative of functions with respect to that vector field should always be 0, and the connection of our sections should also always be 0. So then this gives us our new Hilbert space, which is the set of sections such that the connection of our sections with respect to these vector fields x is equal to 0. That should have an equal 0 in there. So this can be incorporated into our system from before, where we change our line bundle from our pre-quantum line bundle. We include a tensor product with this term here, which the form of it isn't too important. It's what we call a metaplectic correction. And we also change our connection to include this nabla delta, which is the partial connection on our metaplectic correction. So this now acts on sections psi, which is given by the tensor product of s and tau, which gives us a new equation of motion, or in fact, it gives us two equations of motion, where the connection of s should equal 0, as should the partial connection of tau. So these two, however, these two Hilbert spaces are actually isomorphic, so they're identical. So they tell us the same physics. They're just two different ways of representing it. And from this, then we can fix what we had as our pre-quantum operator to a fully quantum operator. We just need to include one extra term, which is a Lie derivative of these sections on our metaplectic correction tau. So this is all very general, so it's a little bit easier to see with an example here. So if we set our polarization to be the set of functions that only dependent on, or the set of tangents based on our momenta, this is called vertical polarization. We can see that if we were to take any elements of our original manifold, the two-form contraction between one element of this and of our general manifold is only zero if they're both in P. So P is a valid polarization. And we can see then that sections of this new line bundle are given by psi, which actually can be reduced further if we introduce unit sections S1 and tau1, which means then that all of our variation is in this function psi, which is the product of our two functions f and g, which are just smooth functions. But if we work through with our equations of motion, the partial connection over tau, over any section tau, with respect to some vector field x, should be equal to 0. But this is simply just the Lie derivative of this function g, which means then for x in P, this just means that the partial derivative of g with respect to P, any P should always be 0. And something similar for our full connection of S, except we see here we have the additional term where we contract our symplectic potential against this vector field. However, if we remember before the form of our symplectic potential, it had a dq term, which is a cotangent vector. The contraction of this against any element of P, as you can see, it has a tangent vectors in the form of tangent vectors. This will always be 0. So this contraction term will always give us 0. So again, it simply says that the Lie derivative of these functions f with respect to these vector fields x is equal to 0. And so our partial derivative of f with respect to these momenta should equal 0. So this simply means we have some function psi or phi, which is not dependent on any of our conjugate momenta. So then we can write this as before in terms of our two real generalized coordinates q plus and q minus, which themselves are only functions of this term theta of t. This means that we can write this function after a Fourier transformation in this form here, where it's some complex numbers ck times this function, our original coordinate phi to the k. And this defines finally our full Hilbert space, which is the set of wave functions psi written in this form, where phi is a function of time only. So there's only one degree of freedom in k. Or sorry, that's not true. So this is our set of wave functions that acts on our Hilbert space. So we can then apply these original coordinates phi and pi to our quantization operator, and they do in fact return as we would expect from quantum mechanics. Our coordinates give us just a multiplicative factor, and our momenta give us a partial derivative with respect to the corresponding coordinate. And similarly, we can do this for our Noether charges for q phi and for our Hamiltonian. But again, they just give us as expected. So this is a valid form of quantization. The interesting part comes when we compare our physical canonical quantization, so the one that was motivated by our understanding of quantum mechanics, with our geometric quantization, specifically in the Hilbert spaces. Whereas the operators seem to all take the same form, the Hilbert spaces we can see are both different. So in our H1, we can see there's both N1 and N2, and these are both natural numbers, whereas our Hilbert space from geometric quantization only has k, which is some integer, and it's written as the set of sections, whereas our original Hilbert space H1 is written as a set of states N1 and N2. So this is just a look at the method of geometric quantization. and some of the differences that arise, but this can be applied to more complicated manifolds. It's just most simple to consider the base manifold given here, because every manifold can be trivialized as well as the line bundles. It can be written in this form locally. So it's best to consider this first, but it can be extended to more complex states. Thank you very much. Any questions? Yeah. So, it's kind of just a way of phrasing it, I believe. So there's some if we take our base manifold M, which has coordinates Q and P, or Qj and Pj, for every point on that, above it, we say there's a one-dimensional complex vector space, which is our would be a line space. So it's kind of like one-dimensional fibers. If we imagine your manifold as kind of a sheet, it'd be like a one-dimensional fiber hanging above it. And if you combine all of those for all points on M, you get another manifold, which is your line. Well, that's not the line bundle, that's the manifold. And then if you combine that with a mapping back from that set of fibers to your base manifold, you get your line manifold or your line bundle. Yeah. Yeah, there's no reason it can't be. It's just a general definition of kind of a mathematical concept. Yeah.
You were talking about flexibility. You said you calculate the curvature.
Yeah.
What does that mean?
Well, if you see here, we have if you look towards the bottom of the slide, we have our connection acting on some section FS1. So we want to see what the curvature of that connection term is. But if we look at the expansion of it, our first term is a Lie derivative, which has zero curvature. So our overall curvature, it's kind of how the manifold twists as you go around it. So our only curvature of this connection comes from our one form A. So we end up where our curvature on this line bundle is just minus dA, which is equal to, there's a little bit of kind of skipping over little parts, but just if we have this connection, if we have this two form omega and our one form A, the curvature on this line bundle is just minus dA, which is equal to our omega. So it's just a situation where it is valid to quantize it in this way.
Did you get a chance to look at slightly more complicated situations, such as
no?
It's a two-sphere, which is angular momentum.
I looked at that more classically, but in terms of promoting it, I didn't get a chance to look at that.
Okay, no more. Oh, how do I actually see what the inner products space is like? Where is that?
So there's in the Hilbert space, there's one other part that didn't come in quite as much. You have a Hermitian metric. So if we're being completely rigorous, to define our pre-quantum line bundle, it's not just our manifold L and our connection nabla, there's also a Hermitian metric, which enforces self-adjointness. That's another way of defining it. But just in general, that kind of goes into a whole other part of the detail about the integrability of these situations that I didn't have time to cover in this presentation. But
so, would I be right in saying that essentially polarization, like a choice of polarization and choice of metric, would be somehow equivalent? Can I see that?
I don't believe so. I think even without polarization. So the issue with the pre-quantum Hilbert space isn't that it isn't valid, it's just nearly too large. So there is an inner product defined over it. It's just that we know from quantum mechanics, we have position space or momentum space. We have representation spaces where they only need, if you have a manifold, a 2n dimensional manifold, it only takes n coordinates. Whereas at the end of this, we have no restrictions on our set of sections. So our general form of sections takes 2n variables, position and momenta. So it's an extra way of reducing the Hilbert space to its lowest or its smallest set, nearly. The need for polarization or the want for polarization comes from the Lie algebra of the pre-quantum operator when you act it on position and momenta. It's not at its lowest. It's too large, or it's not too large, but it's larger than it can be. It can be reduced further. So it's more of a want than a need, but it could be important in more complex situations.
But as in, if I have picked an inner product that's compatible with my symplectic form, then expect the space to be already specified freely without picking already. But I probably just don't understand.
Polarization is essentially like picking what you mean by X versus P. You're talking phase space. So you want to decide what your space is versus your momentum. Abstractly, you don't know that.
If I think about doing this like the old-fashioned way, I would have symplectic space, and then if I had a compatible inner product with the symplectic form on my symplectic manifolds, then this thing is somehow already telling you what the Hilbert space is, right?
Yes, in a sense, yes.
So then what is the
In a
polarization?
sense, you know what the difference is between X and P in that sense. But G has just a lot, they have just a lot of null vectors in that you want to get rid of.
Somehow like
fair way to say it. You just have an awful lot of things that, goes in about the zero, which you don't care.
Oh, right, okay. Oh, it's okay, so you're essentially modding out like some
The zeros.
yeah, okay, I get it.
Okay, so let's thanks again. At 2:30 after lunch.